Hey everybody, Jake here, coming at you today with the classic related rates ladder problem example. I'm sure you've seen a problem like this, typical example of, a ladder sliding down a wall. And today I'm going to be showing you exactly how to solve this kind of problem, step by step. Before we jump into it, I just want to point out once again, this is another example of a related rates problem where you're going to use the same 4 steps that I use in all my other related rates videos. If you go through this problem and you're still a little stuck and confused on how to solve a related rates problem, go check out my other related rates videos and you'll see that they all go through this same 4-step process. So here's the problem that we're going to be doing today. The problem tells us the top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. And then it asks, how long is the ladder? So like I said, it's going to follow the same 4 steps as I solve all related rates problems. The first of those 4 steps is to draw a sketch of what you're dealing with. So let's go ahead and draw what we have described to us here. So first of all, the situation that was described in the problem is that we have a ladder leaning up against a wall and it's sliding down the wall over time. So let's just kind of draw. So we have our wall and then the floor. So we'll say that our ladder is leaning up against the wall, touching down to the floor. So here's our ladder. And as it's sliding down the wall, this here, so we'll say that the ladder, as it moves, it's still touching the wall at the top and touching the floor as well. So basically this point that's touching the floor here is moving this way, and then this point that's touching the wall here is moving down. Okay, so you can see essentially what we have here. The problem did also tell us that this is a vertical wall. So what that means is that the angle between the floor and the wall is 90 degrees. So you can see we basically have a right triangle here. So you can see this right triangle, which is made up by the wall, the floor, and then the ladder. And as the ladder slides down the wall, since it's going to continue touching over here and then over here, we're going to end up with another right triangle. As time goes on, it'll just be different dimensions, basically. But in either case, no matter what point in time we're at, and as this slides away, we're going to still have a right triangle as this goes on. But we'll just consider this snapshot in time where we have the ladder where it is here. So then let's think about the other pieces of information that we're given. We know that the ladder is sliding down the wall at a rate of 0.15 meters per second. So what that tells us is this point here is moving down at a rate of 0.15 meters per second. And we also know at the moment that the problem is describing, essentially the moment when this snapshot is taken, we're looking at the moment when the bottom of the ladder is 3 meters from the wall. So when this distance here is 3 meters. So then the last piece of information it gives us is at this moment when the ladder is 3 meters away from the wall, we know that it's sliding away from the wall at a rate of 0.2 meters per second. So basically this point is moving this way at a rate of 0.2 meters per second. So we know the rate that this point is moving, or the rate that this side length is shrinking. We know the rate that this point is moving, which would be the rate that this side length is lengthening. And we also know the length of this side at this moment. We do not know the length of this side at this moment. And we also don't know the length of the ladder. So this sums up, what's going on, what's being described, and all the information that we are given. So this is a pretty good sketch. We'll go ahead and continue on with this. So now we need to go on to the second step of a related rates problem, which is to come up with our equation. So like I do in all my other related rates videos, what we want to think about is what our equation has to have in it, what distance, what volume, what measurement our equation needs to have in it based on what the question is asking us to find. And then we also want to figure out what we can put in our equation based on what information we actually have. And then what things we want to avoid putting in our equation because we just don't have enough information about it. If you put things in your equation that you don't have any info on, you're not going to be able to use that to actually solve the piece that you need. The best place to start is to first figure out what has to be in your equation. So in other words, what is the question asking us to find? The question asked us, what is the length of the ladder? So basically we need to find, if we imagine this right triangle here, as it changes throughout time, this side is lengthening, this side is shrinking, but our ladder is what's making up this hypotenuse of our triangle, or this long side here. The ladder is obviously not changing. It's always going to be the same length. We have to figure out what that length is. So we know that this side length has to be in our equation. So as a result, what we want to do is label that side something so that we can put that variable in our equation. So let's just say that we will call this side length z. We can call it whatever we want, but let's just go with z. So we know that we need this side length to be in our equation. So this is the one thing that our equation absolutely has to have in it, is z. Because if we don't put this side length in there, that represents the length of the ladder, we're never going to get anything that's going to help us figure that out. So now what we also want to think about is what other pieces we kind of know some information about. Those are going to be the pieces that we want to put in our equation since we actually know something about it. We can use the stuff we know to figure out what we don't know. So what we know about is the length of this side, this lower side, and not only its length, but also how fast it's changing, how fast it's increasing. Remember, our equation that we come up with in this step, it should not have any rate of change in it. It shouldn't have any, anything to do with time. We only want measurements of distance or volume or, some sort of quantitative measurement. We don't want how fast things are changing. We don't care about how they're changing yet. We'll worry about that in the third step. But for now, we just care about the actual length or volume or mass or distance or whatever it may be, the actual physical measurements of what is being described in our sketch from the first step. So as a result, since we do know information about this side length and also how much the side length is changing, that those are both relating to the length of this side at this time. So that tells us that the length of this side is something that would be helpful or that we can use in our equation. So we will need to label that side as well. We'll just go ahead and call it x. So x is another piece that's going to be okay to put in our equation because it's a side length. It doesn't have anything to do with how quickly anything is changing, and we have information about it, and we also have information about how it's changing, which will be helpful later on. And lastly, we also have some information about this side length here. So at this moment that we're looking at, we don't actually have the length of this side, but we are given information about how the length of this side is changing, how quickly it's shrinking. So later on, we're going to have to take the derivative with respect to time of our equation. When we do this, we're going to introduce something that represents how quickly these variables are changing. Since we actually do have information about how quickly this side length is changing, that tells us that we want to include this, or that we can include this side length in our equation, because once we take its derivative, we are going to have information about how it's changing that we can use along with the derivative. So our equation should not include the rate of change of this side, but since we have information about the rate of change of this side length, we can include the side length itself in our equation. So let's go ahead and call this side over here y. So we can include y as well. Z has to be in our equation, and x and y are both things that we can put in our equation that would be helpful. We don't really have any information about either of these two angles, so coming up with an equation that relates the angles of the triangle to the sides of the triangle may not be particularly useful here. The fact that this is a right angle, though, is helpful because that tells us that we can use Pythagorean theorem. Pythagorean theorem essentially just relates the side lengths of a right triangle. What it tells us is that this side length squared will be equal to this side length squared plus this side length squared. So Pythagorean theorem tells us that since we have this right triangle, that's important, this will only work on a right triangle, we can say that our hypotenuse squared, so z squared, is equal to each of our other two sides squared and added together. So x squared plus y squared. So that's just Pythagorean theorem. So this is a perfectly good equation for us to use because it doesn't include any of the angles, which we don't know anything about. It only includes the thing that we needed to find and other things that we have some information about. So this is a perfect equation that we can use going forward. So now that we came up with our equation, we can go on to the third step, which is the same third step as all my related rates videos, and that is to implicitly differentiate or apply implicit differentiation to this equation. So let's go ahead and do that. So we have our equation here, z squared equals x squared plus y squared, and what we want to do is do implicit differentiation. So what we're going to do is we're going to take the derivative with respect to time of both sides of this equation. So we're taking the derivative with respect to time. This symbol here just means take the derivative with respect to time. So the fact that we have a t right here, we're taking it with respect to time, that tells us that we are going to be taking the derivative of both sides of this equation and treating t as the variable. So what that means is any other letters that you see in there, any other letters that aren't constants, will be treated as a function of time. We don't know what the function is. We just know that it's a function and that it depends on time. Notice I said all letters that aren't constants. The reason why that's important is if we have a letter in our equation which represents a constant, so in other words, the thing that that letter represents is not changing over time, it's a constant length or weight or distance or whatever. If it's a constant, we can treat it like a constant. The derivative of a constant is 0. So that might help make things easier for us. But anything that's not a constant, anything that's changing, we need to treat as a function of time, where basically t is the input variable of that function. So let's think about each of these three letters here. Obviously, none of them are t, none of them are time. But notice z represents the length of the ladder. Well, the ladder is not changing. The ladder is always going to be the same length. Even as it slides down, it's always going to stay the same length. So what that means is z is actually not changing over time. Z is always going to be the same number no matter whether we start it, whether we look at it when the ladder is way up here or as it slides close to the ground, z is always going to be the same number. So what that means is if we're taking the derivative of z, well, in this case it's z squared, but a constant squared is still going to be a constant, right? Think of, imagine z was any number, let's just say z was 10, 10 squared would just be 100, it's still 100, it's not changing. So squaring it doesn't change the fact that z squared is going to be z squared no matter what point in time we're looking at. Z squared is not going to change over time. So as a result, if we take the derivative with respect to time of z squared, that's just going to be 0. The derivative of a constant is always 0. So that helps make our equation a lot easier because now we don't have a z or a dz dt to worry about. We're only going to have x's and y's. However, x and y are not going to be as easy because y and x are both changing over time, right? As the ladder slides away from the wall, x is going to increase, and at the same time the ladder is sliding down the wall, which will make y decrease or shrink. So x and y are both changing, which means they're not constants. And as a result, since we're taking the derivative of them with respect to time, we need to treat them as functions of time. But we don't know a function for x and y, so we can't get an explicit function for the derivative of x and y. So that's why it's called implicit differentiation. We're getting kind of an implicit formula that relates these derivatives together. But the point I'm making here is, since x and y are both functions, when we take the derivative of x squared and when we take the derivative of y squared, we're actually going to have to use chain rule for both of those. The reason for that is you want to think of x as being some function of time. So real quick, we'll come over here. Let's imagine we have some function of time. Let's just say this is x. But if we're taking the derivative of this function of time all squared, we would have to use chain rule, right? We wouldn't just be able to move the 2 down in front and use the power rule. We would have to do chain rule, which is take the derivative of the outside, so bring the 2 down in front, leave the inside alone, lower the power by 1, and then by chain rule, we would also have to multiply this by the derivative of the inside, which is just going to be f prime. So we have to apply this same idea to x squared over here. We don't know the function for x because it's some unknown function of time, but we know it's a function, and therefore we have to treat it as a function all being raised up to the second power. So like we just did over here, we're going to take the derivative of the outside, so bring the 2 down in front, leave the inside alone, lower the power by 1 by the power rule, and then we have to multiply this by the derivative of the inside. Our inside is just x. X is our entire inside function. The derivative of x with respect to t is not 1, but it's going to be dx dt, which just means the derivative of x with respect to t. So now we can do the same thing with y squared, and it's going to work out basically the same, except our inside function now is going to be y instead of x. So if we bring the power down in front, leave the inside function alone, lower the power by 1, and then multiply by the derivative of the inside. So these powers here are both the number 1. It's not y prime and x prime. So just to kind of simplify this, we would have 0 equals 2x dx dt plus 2y dy dt. Okay, so now we've done our implicit differentiation step. We've taken the derivative of both sides of our equation that we came up with in the second step and got to this point. So now we can go on to the fourth step of a related rates problem, which is to solve for the desired rate of change. This one's a little weird because we aren't really solving for a rate of change. Our question wasn't asking us to find a rate of change. It was asking us to find the length of the ladder. However, to find that, we're going to need to take this equation and solve it for y. And the reason we need to find y is we can use our original equation, right? We know that z squared equals x squared plus y squared. We already know x in this moment is 3, but we don't know what y is and we don't know what z is. So these two things are unknown. We know what x is. If we found y, we could use this equation along with our known value for x, value for y we figure out. We can use those to figure out and solve for z. Since we don't have any information about the angles of this triangle, and we only know this one side, which is x, we instead have to use this equation, and we can solve this equation for y. And the reason for that is we know what x is, right? It's 3. We also know how quickly x is changing, which is exactly what dx dt represents. That's given here. We also know what dy dt is, which is how fast y is changing with respect to time, which is this has to do with this measurement here. So we have the 3 other pieces of this equation, but we don't have y. So we have this one equation, we can plug in all those other things for y, or I'm sorry, we can plug in all those other things for x, dx dt, and dy dt, and then get y all by itself. And then once we've figured out what y is, we can take that and plug it into this equation to find z. So it's not exactly a rate of change we're looking for here, but we do need to use the rate of change, the rates of change that we do know and that we were given in this equation to find another value that's also in this equation. Let's go ahead and plug in the values that we know. So we know that our side x in this moment is 3 meters. We also know that our side length x is increasing because the ladder is moving away from the wall. Since x measures the distance between the ladder and the wall, as that moves away, that distance will get longer. So that means that dx dt is 0.2 meters per second. Then we'll have 2y. Y we don't know, but we do know dy dt. So as the ladder slides down the wall here, this distance, which is y, which measures the distance between the floor and the top of the ladder, this distance is going to shrink as the ladder moves down the wall. So as that happens, we know that it's moving down at a rate of 0.15 meters per second. Since y is decreasing because this distance is shrinking over time, dy dt should be a negative number because it's getting smaller. Since it's getting smaller by this rate, dy dt would be negative 0.15. So now that we've plugged in all those values, we can solve for y. So first we'll just kind of simplify this. 2 times 3 times 0.2 is 1.2. And then 2 times negative 0.15 is negative 0.3. And then we'll have our y there still. So now we can add 0.3y over to the other side of our equation. So we'll have 0.3y equals 1.2. Then we can divide both sides by 0.3. That'll cancel. So we'll get y equals 4. So we know that at this moment, y is 4. So this side here is 4 meters. This side here is 3 meters. So now if we go to this equation, z squared equals x squared, which is 3 squared, plus y, which is 4 squared. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. So now we can take the square root of both sides, and we'll get z equals 5 meters. So we know that z, which is the length of our ladder, is 5 meters long. So like I said, I do have lots of other related rates videos. I recommend you go check those out now. It'll give you a good range of different problems and practice problems having to do with related rates. So you can see, all sorts of other geometric shapes like cones, cylinders, couple sphere, there's all sorts of other different related rates problems and examples that I have. So go check those out. I'll link them right here. Go check those out while it's fresh in your mind, so you can see all these different examples. and hopefully they'll help really kind of cement these 4 steps that you can apply to any related rates problem, kind of cement those into your head. So go check them out. Thanks for watching. Hope to see you back soon.